Imagine the distant future. It's the year 2500. Humanity has finally sent its first probe beyond the Milky Way, a historic achievement. The sleek spacecraft, named Wanderlust 1, is intended to reach Andromeda, our nearest galactic neighbor. A live broadcast streams to billions across settled planets in the solar system and beyond. A momentous occasion, a triumph of human engineering and determination. But just as the onlookers celebrate, something catastrophic happens. Impact. The middle of the probe crumples inward like an invisible fist has struck it. Metal warps. Sections twist. Parts vanish entirely, erased from existence as though edited out of reality itself. The probe's systems short out. Its spinning remains become nothing more than cosmic debris, and then the culprit becomes clear. Wanderlust. I wasn't hit by a meteorite. It wasn't destroyed by radiation or solar flares. It was struck by a primordial black hole. A microscopic singularity, smaller than a proton, yet possessing a mass equivalent to an adult white rhinoceros. Scientists call these objects black hole rhinos. This is fiction, but only partially. The scenario describes something that could happen. And new discoveries from the James Webb Space Telescope suggest that such tiny black holes might not be as implausible as we once thought. In fact, they might be out there right now, orbiting through space, circling our galaxy's edges, silent, invisible, waiting. The James Webb's latest findings hint that the universe might be far more dangerous and far stranger than we ever imagined. Part 2. Ordinary black holes. Until recently, our understanding of black holes was relatively straightforward. Black holes form when massive stars reach the end of their lives. When a star with a mass of at least 20 times that of our Sun exhausts its fuel, it collapses. The core implodes with such catastrophic force that gravity overwhelms every other force in physics. Electrons are crushed against protons. Neutrons are crushed into neutrons. Matter compresses to densities so extreme that the escape velocity exceeds the speed of light. That event horizon, the boundary beyond which nothing can escape, defines what we call a black hole. These are stellar black holes, born from the death throes of massive stars. They range from a few solar masses to perhaps a few hundred. The process is well understood. Stellar evolution predicts their existence. Astronomers have cataloged many candidates. Smaller stars follow different paths. Those with masses between 8 and 20 solar masses go supernova, but don't collapse into black holes. Instead, they leave behind neutron stars, bizarre objects so dense that a teaspoon of their material would weigh as much as Mount Everest. These stellar remnants are extreme, but they're not points of no return. This model of stellar mass black hole formation works well. It explains the black holes we've detected in binary systems. It's supported by centuries of observation. But there's a problem with this model, a fundamental limitation built into the system itself. According to our best understanding, stellar black holes can't be arbitrarily small. There's a minimum mass determined by the physics of stellar collapse. You can't have a black hole the size of an atom. You can't have one that weighs as much as a rhino but exists in a volume smaller than a proton. Or so we thought. Part 3. The supermassive paradox. The first real challenge to our black hole orthodoxy came from an unexpected direction, not from tiny black holes, but from enormous ones. Nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its core. These objects are titans. Sagittarius A, the black hole at the center of our galaxy, weighs about 4 million times as much as the Sun. The largest known black holes weigh billions of solar masses. For decades, astronomers assumed these supermassive black holes grew from stellar seeds. Small black holes, born from dead stars, would accrete matter from surrounding gas and dust. Over billions of years, multiple mergers would occur as smaller black holes collided and merged into larger ones. Eventually, through this gradual accumulation, tiny stellar mass black holes could grow into galactic titans. Theoretically, it's possible. The math works out. But there's a catch. When the James Webb Space Telescope pointed its instruments at the early universe, looking at light that began its journey when the cosmos was less than 1 billion years old, it discovered something shocking. It found galaxies hosting supermassive black holes. Not small ones, not moderate ones, true titans. Black holes with masses in the millions or even billions of solar masses. But there simply hasn't been enough time for those black holes to grow from stellar seeds. The numbers don't work. If you feed a stellar mass black hole at the maximum theoretical rate, much faster than observed in reality, it still can't accumulate enough mass to reach these scales in the available time frame. One particularly striking example is A2744 QS01, a supermassive black hole discovered by Webb. It resides in a galaxy remarkable for its chemical simplicity. The galaxy is almost entirely composed of hydrogen and helium, the primordial elements created during the Big Bang. Heavy elements like oxygen, carbon, and iron are nearly absent. These heavier elements are produced by stars and distributed through galaxies during supernovae and galactic outflows. The fact that QS01's host galaxy is so chemically primitive suggests that it has undergone very few stellar generations. Barely any stars have lived and died there. And yet, somehow, this young galaxy hosts a supermassive black hole. This is the paradox. Either 1. Our models of stellar black hole formation and growth are fundamentally flawed, or 2. Black holes have another way to be born, a way that doesn't require stellar ancestors. Part 4. The Big Bang Connection. The solution to this cosmic puzzle reaches back to the very beginning of time. In 1966, Soviet physicists Yakov Seldovich and Igor Novikov proposed a revolutionary idea. What if, they asked, black holes could form not from stellar death, but directly from the matter of the early universe itself? In the first fractions of a second after the Big Bang, the universe was unimaginably hot and dense. The entire cosmos existed as a roiling sea of elementary particles and radiation. The density was so extreme that matter couldn't maintain its normal properties. Protons and neutrons couldn't form stable atomic nuclei. Electrons couldn't orbit nuclei. Everything was plasma, a quantum soup hotter than anything that would ever exist again. Crucially, this early universe wasn't perfectly uniform. Like ripples in a pond, quantum fluctuations created regions of slightly higher and slightly lower density. These density variations were small, perhaps 0.01% variations in local mass density, but they had consequences. In the densest patches, gravity could overcome all other forces. Those dense regions could collapse directly into black holes without waiting for stars to form, live, and die. The collapse would happen in microseconds. The resulting objects would be primordial black holes, born directly from the Big Bang substance. The remarkable aspect of primordial black holes is that they could form across an enormous range of masses. Giant primordial black holes. With masses of hundreds of thousands of solar masses, these could serve as the heavy seeds that evolved into today's galactic black holes. Exactly what we need to explain Webb's observations. Intermediate primordial black holes. with masses ranging from thousands down to kilograms. Microscopic primordial black holes, with masses equivalent to mountains, to cities, to individual buildings. Ultra-tiny primordial black holes, smaller than any human-made object. The famous black hole rhinos, approximately the mass of an adult white rhinoceros, around 2 tons, but compressed into a volume smaller than a proton. If primordial black holes exist, some black holes in the universe today are older than stars, older than galaxies, older than any other massive objects we can imagine. They're relics of the first instant of creation. This changes everything about how we understand the cosmos. Part 5. Webb's Strange Discoveries. For decades, primordial black holes remained theoretical, interesting mathematically, but lacking observational confirmation. Then came James Webb. Launched on Christmas Day 2021, this infrared observatory has revolutionized our view of the early universe. Its instruments are sensitive enough to detect the light from stars and galaxies formed just a few 100 million years after the Big Bang, an epoch entirely inaccessible to previous telescopes. Webb has found 2 discoveries that strongly suggest primordial black holes might be real. Discovery 1. The Infinity Galaxy. In mid-2025, astronomers analyzing Webb data identified 2 young disk galaxies in the process of merging, crashing into each other at tremendous speed. Between these 2 galaxies, separated from either one, astronomers found a supermassive black hole with a mass around 1 million solar masses. This is peculiar. Each of the 2 merging galaxies hosts its own central black hole, as most galaxies do. But this third black hole sits in the void between them, belonging to neither galaxy. How did it get there? The most plausible explanation: it formed in situ, directly within the intergalactic medium through a process called direct collapse. A particularly dense gas cloud, isolated from any galaxy, accumulated enough mass and density that it collapsed directly into a black hole without requiring a stellar precursor. This matches perfectly with primordial black hole formation mechanisms. If the early universe could produce such heavy seeds directly from matter, perhaps the mechanisms described by Zeldovich and Novikov were operating. Discovery 2. QSO-1's chemical innocence. The other example comes from Webb's detailed spectroscopic analysis of QSO-1's host galaxy. Spectroscopy reveals the galaxy's chemical composition by analyzing the light it emits and absorbs. The results were stunning. The galaxy is chemically unevolved. It has less than 1% of the oxygen present in our own galaxy. Essentially no carbon, almost no metals. In astronomical parlance, metals means any element heavier than helium. The galaxy is composed almost entirely of primordial material, hydrogen and helium, from the Big Bang itself. This is extraordinary because heavy elements are produced by stars. In a galaxy that has undergone multiple generations of star formation, these elements accumulate over time. The presence of heavy elements indicates an old galaxy with substantial stellar history. The absence of heavy elements indicates the opposite: a young galaxy, one that's barely begun forming stars. Yet in this chemically primitive galaxy orbits a black hole of 10 million solar masses. For stellar processes to create such a black hole in such a young system would require extreme efficiency and favorable conditions. Primordial black hole formation offers a much more natural explanation. Part 6. The dark matter connection. Having established that primordial black holes likely populated the early universe, and that giant primordial black holes may seed today's galaxies, a natural question follows. What about the tiny ones? If the Big Bang, could manufacture seeds for galactic black holes, it almost certainly also created vast numbers of much smaller black holes. According to primordial black hole formation theory, there should be a population of very small objects, perhaps outnumbering all the larger black holes combined. But where are they? This question connects to one of cosmology's deepest mysteries: dark matter. We know from observations of galaxies and clusters of galaxies that the universe contains far more mass than visible in stars, gas, and other luminous material. When we measure the motion of stars orbiting galaxies, their orbital speeds indicate gravitational pulls from masses much greater than what we can see. When we observe how light from distant galaxies bends as it passes through clusters of galaxies, the bending indicates gravitational effects from far more matter than the visible galaxies account for. This invisible mass is called dark matter. It comprises roughly 85% of all matter in the universe, yet its fundamental nature remains unknown. Is it an undiscovered elementary particle? Is it primordial black holes? Some combination? An intriguing possibility. What if dark matter is largely composed of tiny primordial black holes? If a significant fraction of the dark matter in galaxies and galaxy clusters consists of microscopic black holes, objects too small and dark to observe directly, it would explain the gravitational anomalies we observe, provide a natural home for primordial black holes, represent one of the most profound discoveries in physics. But there's an obstacle: Hawking radiation. In 1974, Stephen Hawking demonstrated theoretically that black holes aren't perfectly black. They emit radiation. The smaller a black hole, the more quickly it radiates. Through this quantum process, black holes gradually lose mass and eventually evaporate entirely. According to Hawking's calculations, microscopic black holes formed 13. 8 billion years ago should have evaporated long ago. By now, all the tiny primordial black holes should be gone, vanished in bursts of Hawking radiation. Except a 2024 study published in the monthly notices of the Royal Astronomical Society proposed something unexpected. At extremely small mass scales, Hawking radiation might not behave as initially predicted. The rate of evaporation could slow dramatically, potentially nearly halting. If true, some primordial black holes, the rhinos, the asteroid mass objects, even mountain mass ones, might have survived until today. Part 7. The Invisible Minefield. Imagine for a moment that we're correct. Imagine that the early universe created not just giant primordial black holes, seeds for galaxies, but vast numbers of tiny ones. Imagine that Hawking radiation slowed at small scales, allowing many of these objects to survive 13.8 billion years. What would the consequences be? First, consider your local galactic neighborhood. Our Milky Way, like all large galaxies, is surrounded by a halo of dark matter. This halo extends far beyond the visible disk of stars, perhaps hundreds of thousands of light years outward. Its mass greatly exceeds the mass of all visible stars and gas combined. If a significant fraction of this dark matter halo consisted of primordial black holes, then our galaxy would be surrounded by an invisible minefield. Millions, perhaps billions, of microscopic black holes distributed throughout the halo, winding through space. Most would go entirely undetected. A black hole with no accretion disk, no gas spiraling into it, producing friction and radiation, emits nothing. It can't be seen directly. Its gravitational influence is localized. It only significantly warps space-time in its immediate vicinity. We might detect some through indirect means, gravitational microlensing, The black hole's gravity slightly bends the light from stars behind it. Stellar disruption. A star's orbit becomes chaotic if it passes too close to a black hole. Gravitational wave detection. If two black holes collide, they create ripples in spacetime. But for many of these objects, we would see nothing. They would drift silently through our galaxy, through the spaces between stars, and we would never know. This scenario has profound implications. If the space between galaxies is filled with primordial black holes, then intergalactic travel, a goal of distant future civilizations, becomes a gravitational hazard. What appears as empty void is actually a minefield of ancient singularities. Perhaps this is why we don't see signs of advanced alien civilizations filling the galaxy and beyond. Perhaps the apparent emptiness of nearby space reflects not the rarity of life, but the abundance of gravitational hazards that make sustained interstellar expansion lethal. JWST Part 8. Risk Assessment. To put this in perspective, we should consider the actual danger. The scenarios described above, probes destroyed by primordial black holes, catastrophic encounters with microscopic singularities, sound terrifying. And they are in fiction. The reality is somewhat less dire. Statistically, space is vast beyond human comprehension. The distances between stars are so immense that even if primordial black holes were scattered throughout the galaxy, the probability of a specific spacecraft encountering one would be extraordinarily small, smaller than many everyday risks. Additionally, if a probe did encounter a rhino mass black hole, it wouldn't instantly vanish. The black hole's gravity would distort the probe's structure, potentially tearing it apart through tidal forces. But this would happen over measurable distances, not instantly. The deeper concern isn't immediate collision. It's epistemological. If much of the universe's mass consists of objects we cannot directly observe, our fundamental understanding of reality is incomplete. We build models. We test them against observations. We refine them. But if the majority of matter hides from our instruments, our models, no matter how refined, rest on incomplete foundations. This is the genuine unsettling aspect. Not that we might hit a black hole, but that we've likely been wrong about the composition and structure of the cosmos itself. Part 9. Webb's Legacy and Future Investigations. James Webb hasn't directly imaged a primordial black hole. It hasn't provided definitive proof that they exist. What it has provided are tantalizing clues that primordial black holes might be more common and consequential than previously assumed. The evidence includes supermassive black holes appearing in the early universe at unexpectedly large masses. Objects like Infinity Galaxy, suggesting direct collapse black hole formation, chemically primitive galaxies hosting massive central black holes, the persistence of dark matter as a cosmic mystery. The next chapter in primordial black hole research will involve advanced direct collapse models, understanding the precise conditions under which gas clouds can collapse directly into black holes, and whether such conditions were plausible in the early universe. Micro-lensing surveys. Telescopes and instruments designed to detect the subtle light-bending effect of microscopic black holes passing in front of distant stars. Gravitational wave detection. The LIGO and Virgo observatories and future space-based detectors like LISA could potentially detect gravitational waves from primordial black hole mergers. Core collapse supernova studies. Refining our understanding of the maximum masses of stellar black holes, which helps constrain how many supermassive black holes could form through stellar channels versus primordial channels. Each advance brings us closer to a definitive answer. in perhaps another decade or two, we may know whether primordial black holes constitute a major component of the universe's dark matter, or whether they remain rare relics of the earliest moments. Part 10. Philosophical Reckoning. But beyond the scientific questions lies something deeper. A question about our place in a cosmos that grows stranger with each new discovery. For centuries, humans assumed we understood the fundamental building blocks of reality: matter, energy, the basic forces. This confidence shaped our philosophical worldview. We felt we grasped existence at its core, even if we didn't fully comprehend all its complexities. Relativistic quantum mechanics refined our understanding. The standard model of particle physics unified our descriptions of elementary forces, but these advances broadened our understanding without fundamentally challenging our worldview. We added layers to our model. We didn't overturn it. Primordial black holes, especially if distributed throughout galaxies as dark matter, would represent something different. They would suggest that the universe is not just complex, but fundamentally mysterious in ways we haven't appreciated. Imagine a revised picture of the cosmos. Galaxies spin through space, visible and beautiful. Within them, trillions of stars shine. Between the stars, vast clouds of gas form new solar systems. Planets orbit those stars. Life emerges on some worlds. But underlying this visible universe is another realm, a realm of invisible singularities, relics from the moment of creation, black holes woven into the fabric of existence, shaping gravity, anchoring dark matter, fundamentally determining the structure of space-time. We navigate this realm blind, aware of its gravitational effects, but unable to observe its constituent parts directly. It's a humbling realization. Despite centuries of progress in astronomy and physics, we may still be missing the majority of what the universe contains. The cosmos we can see, every star, every galaxy, every visible phenomenon, might be merely the ornament on a structure whose main architecture remains obscured. We gaze at the night sky and see beauty, nebulae, galaxies, stars. But beneath this beauty may lie invisible singularities, a universe built on structures we cannot see. If this thought makes space feel less cozy, you felt what Webb's astronomers experienced. This is wonder, not despair. The cosmos still surprises us. Subscribe for more explorations of black holes, the early universe, and cosmic mysteries. We remain in the Milky Way's Orion arm, asking, what else lurks unseen?